Number 74. Calculate the concentration of each species present in a 0.01 molar solution of phthalic acid, which is C6H4CO2H2. Okay, thank goodness they gave us the balanced equations because this would have been a little rough, right? But I think it's going to be a little rough anyway, so strap in those seatbelts. But we got this, right? So since there's two different balanced equations here, we know that phthalic acid is a diprotic acid. Di means two, product means protons. So basically, you have two Ka values for each proton or each hydrogen that you lose. So since this is phthalic acid, C6H4CO2H2, and then it's stated right here, identically, this Ka value would be the first ionization constant, and then the second balanced equation would be the second ionization constant when you lose that second proton. So we have to work from top to bottom. So we always work with K1s first, and then we work with the K2 equation. So one at a time. So what I'm going to do is I'm just going to replicate this. So we have C6H4 CO2H2, and that's aqueous, plus water, and that's a liquid. This is a weak acid, so it's at equilibrium with, now they're saying H3O plus, beautiful, that's aqueous. And then C6, the conjugate base, H4, C, O2H, and then CO2. Jeez. Okay, minus it, that's aqueous. All right, so I'm just going to pull this over. Beautiful. And now, since they only told us that we're starting off with a 0.01 molar solution of just phthalic acid, that's an initial concentration. And anytime that they give us an initial concentration with a weak acid, we know that we have to do an ice chart. So let's do that. That actually didn't come out that bad. Let's see. Bring this a little bit down. Red for acid, so ICE, that's just my preference. And remember, liquids are not allowed in the Ka expression. So we used it to get the hydronium ion, but we don't care about it in terms of the actual math, so just get rid of this column. It just makes life much easier. Okay, so initially they told us that we had 0.01 molar of the phthalic acid. That's this one. So I have 0.010. Thank goodness it's already in molarity, right? They didn't state that I started off with any hydronium, or they didn't state that I had any of the conjugate base, so I have to assume that I had none. And that makes it easy for the change, right? C stands for change, the change in concentration. If you started with nothing, you can only go up from there. So since I have nothing on my products, I know that the change has to increase in concentration, plus. And that means that on the reactant side, it's got to be minus. We don't know by how much, so we like to use the variable. Pick any variable. I'm just going to use x. So minus x, and plus x. And good thing with acids and bases is that it's always going to be a 1-to-1 ratio. There's no coefficients in the front, so you don't have to worry about 2x or 3x or any of that stuff. E stands for equilibrium. We're just taking the initial and the change together. So it would be 0.010 minus x, and x. Okay, beautiful. Now, since we have our equilibrium line, remember these are the only things that go into the Ka expression. And since we're using the first balanced equation, we got to use the Ka1. But then, remember, in general, Ka equals something divided by something, right? Concentration of the products divided by the concentration of the reactants. So in here, let's see, if I just set this up, the Ka would equal H3O plus times that conjugate base on the product side, C6H4 parentheses CO2H, oh boy, cutting it a little close here. Let's maybe bring that out a little bit. CO2, and then minus, right? There we go. And then the phthalic acid on the bottom. I'll just bring this out a little bit. C6, H4, CO2H2. Okay, so now we're just going to put in the numbers. 1.1 times 10 to the negative third equals something divided by something, right? We got two things on the top being multiplied by each other and one thing on the bottom. So H3O plus was X. The conjugate base was also X. And now here's the issue, guys. This minus X, if we have to include it, it's going to give us the quadratic equation, which we try to avoid at all costs. Now, I'm looking at this Ka value, and it's 10 to the negative third. That's not really too low. Throughout this whole chapter, we've been seeing Ka's as low as like 10 to the negative 11th. A low Ka value means that at equilibrium, you have mostly reactants. So in this case, we started with all reactants, and if it's just low enough, we would end with mostly reactants. So let's just see if we can negate this change. If it's small enough, the change is so small, it's like this small, that the numbers between initial and equilibrium would probably stay the same. So we're going to try that out first, and then we're going to do a check to see if we can do it. If not, we got to do the quadratic. So fingers crossed, guys. Let's see. So I'm going to just solve for X. So cross multiplication, right? The Ka times this number equals X squared. So X squared equals, calculus out, 1.1 times 10 to the negative 3 times 0.01. And I get 1.5 times 10 to the negative fifth. Let's square root that on both sides to get rid of that square. Okay. And since we're getting a couple of answers here, let's keep it into 2 sig figs. So 0.0033. Now here is the trick, or the little check that you're going to do to see if we can negate this X. What you're going to do is we're going to play the 5% rule. And what the 5% rule is that you're going to take your answer that you found out, so 0.0033, and you're going to divide it by the initial concentration, which was 0.01, and times it by 100. If the answer that you get is 5 or lower, we were able to scooch by without including that negative X. But if we get an answer that's over 5, we have to go back and say, I can't get rid of that X. So I don't think this is going to be a good one, guys. It's 33%. Way above 5%, which means that we couldn't have stated that that change was negligible. So let's go back. So basically we failed. We failed the 5% rule. Chances more than not you will pass the 5% rule, and then you can just continue with that X value. So we got to go all the way back to this part right here, where maybe I can just get rid of this. I'll get rid of this and get rid of that. Pull this back. And now I have to say that I can't get rid of this minus X. It has to stay here. And because of that, I will include a minus X in here. Okay, so now I'm just going to get rid of the 5% rule. Now when we cross multiply, you might see the problem here, because we're going to distribute, right? Remember, this goes into that and this X value. So I'm going to try to do it in one shot. So let's try it again. 1.1 times 10 to the negative third times 0.01. Did I do this correctly? 1.1 times 10 to the negative third times 0.01. Looks good to me. So 1.1 times 10 to the negative fifth minus, if I do 1.1 times 10 to the negative third times a negative X, it's 1.1 times 10 to the negative third. X equals X squared. This is the problem because I have an X and an X squared. That's the quadratic formula. So remember, quadratic formula, we have to get all of these values on the other side of the equation. So if I just plus 1.1 times 10 to the negative third x on both sides, and by doing the same thing with this c value, I'll minus 1.1 times 10 to the negative fifth on both sides. And what's going to happen is, pause the video. I'm just going to get rid of this math over here. Boop. We're basically going to get 0 equals, because everything on this side is going to cancel, right? So I get 0 equals, the x squared is coming along for the ride. Then the x value, so plus 1.1 times 10 to the negative third x. And if I just move this over for now and bring over the c value, there you go. Now I'm going to get rid of this. And here is my a, b, and c value. Remember, the quadratic equation is this one right here. Yeah. Remember, negative b plus or minus the square root of b squared minus 4ac all over 2a. Love it. So we just got to get our a, b's, and c values here, right? So in this case, if I just color code this, right? Remember, the a is in front of the x squared. There's no number here, which just means that there's a 1. So a equals 1. The b is going to be the number that's in front of the x. Got to keep that sign in there, so it's a positive. 1.1 times 10 to the negative third. And then the c value is just the number by itself. Got to take into consideration that sign, so it's a negative 1.1 times 10 to the negative fifth. These are going to go in here. So now, let's see. Maybe I can pull this over so that we have a little room. And let's see, I think I can make this smaller. So hang tight, guys. Okay, perfect. I'm just going to make this a little smaller. We'll put this right over here because we're going to need it in a little bit. And now I'm going to bring this up so we have all this space to work with the quadratic formula. And basically, I'm just going to put my b's in and my c's and my a's. So x equals, and I'll probably have to move this a little bit down. Okay, so x equals negative b, so negative 1.1 times 10 to the negative third, plus or minus the square root of b squared. So we're going to square that b value, which is 1.1 times 10 to the negative third. Close that up. Minus 4 times a. A was just, how did I say a equals b? A equals 1. I guess I was talking. I was chit-chatting. So, times by 1. Now we have to times by c. And c was, I got to pull this over a little bit. So I think what I'm going to do is I'm just going to keep like erasing because I think that's going to be easier. 1.1 times 10 to the negative fifth. Extend that out. And this now all has to be, oh boy, this all has to be divided by 2 times a, and a was, remember, 1. Okay. So now let's just clean this up here, right? Well, 2 times 1 is just 2. So I'm just going to erase that. That's pretty easy. Now I'm going to have to work and get this under control. Now, technically, if you want to, you can plug all this in at the same time, right? So in the calculator, I'm just going to get this whole thing under the square root as one number. So I'm going to do 1.1 times 10 to the negative 3 squared minus 4 times 1 times a negative 1.1 times 10 to the negative fifth. And I'm going to get one answer. I'm going to keep the radical. I'm not going to do that yet. I'm going to say 1.1 times 10 to the negative third squared. Okay. Then I'm going to say 4 times a negative 1.1 times 10 to the negative fifth. And then I'm going to take that answer and say minus that answer. Okay, so I'm going to erase all of this. I just wanted to show you guys. So we're getting closer. So we have 4.521 times 10 to the negative fifth. Now we're going to do the square root. So I'm going to take that, do the square root of that number. And I'm going to try not to round as much because we're not really at our answer yet. So this would be 0.0067238, whatever, right? 384. Okay. Now at this point, you have two options. This plus or minus says that we could either do this plus this, or we could do this minus this. Now we have to figure out which one is going to give us the positive answer. Remember, there is no such thing as negative polarities. So if I already have a negative, right, and a negative minus this value, I'm going to be getting more negative. So I know that the only one that I can do is the positive value. But you could always just double check. You could do two of the answers, and you'll see that one is positive and one is going to be negative. So now we're just going to do the top. So negative 1.1 times 10 to the negative 3 plus 0.006723884. And I'm just going to erase this. Don't we love doing the quadratic? Ugh, it's like so much fun. Kidding. 0.0562384. And now we just take that and divide it by 2. And now, since we got an answer, we are going to take it as 2 sig figs, because that's what we started with. So if I divide by 2, x finally equals 0.0028. Okay. So now, we have some of our answers, right? X, this is what x equals. Here's x, and here's x. So I'm going to start writing down my answers. So as far as my H3O plus concentration, it's 0.0028 molarity. And the same for that conjugate base. So C6H4, CO2H, CO2 minus, that's also 0.0028 molarity. Now coming back to your phthalic acid, it's 0.010 minus the 0.0028. And that's going to be that concentration. So C6H4, CO2H2. And let's see what that is. 0.01 minus 0.0028. I get 0.0072. Okay, so we have 3 concentrations ready to go. Now we're done with the first part. So we have to do the second part now. So what we're going to do is I'm just going to get rid of this. Pause the video if you need any of the math, but we're going to start afresh. We're going to get rid of these numbers in the ice table because new ones are coming. I'm going to get rid of these because hopefully, fingers crossed, we do not need a quadratic. And I'm going to get rid of this x value. Okay. Now, I'm just going to copy this. But technically, I think there's a typo here. This conjugate base now becomes the acid. So I think they forgot this negative here. Basically, this and this should be identical. So I'm going to get rid of this start. And I'm just going to bring it over. This is what I ended with, and now that's becoming my beginning. But it's still plus H2O. I still get the H3O plus concentration, and then we get C6H4, CO2, 2 with the 2 minus charge, and that's aqueous. Okay, so let's plug in our new initials. And your new initials for K2 is going to be what you have written down here. So now initially, we are starting with this, 0.0067238. 0.0028. H2O, just like before, gets canceled out. H3O plus, did we have any initially? I just scanned here. Ah, yes, we did. The same amount. So that's got to go, 0.0028. And this is the new one. That's not one of my ions that I found for, so that's going to be 0. The same thing as before. If you start with nothing, that side can only go up. So this has to be plus, and this has to be minus. And it would be minus x, and plus x. Let's bring them all together. It would be 0.0028 minus x, 0.0028 plus x, and then just x. Here are my new information to go into the Ka value. So I'm just going to change this up a little bit. This is getting lost. This is now the compound that's down at the bottom. And then I have my new compound right here. So C6H4, CO2, 2, and that's a 2 minus. Now, since we're using K2, Ka2, that's the number we're going to plug in here. 3.9 times 10 to the negative 6 equals something divided by something. We have now, now I still see it again, minus x, and I see a plus x. So let's try to see if we could get away with it. We're going to state that maybe the change isn't that great. We're going to do the 5% rule and cross our fingers that maybe, we'll get lucky this time. So I'm going to say this change is not, great. And the plus x is not great. I can't get rid of this x because you have to have an x in the variable, but you can basically get rid of all the change x's, minus or plus x. So then coming in here, this would be 0.0028 times x divided by 0.0028. Oh, this is so easy because I have the same number on the top of the bottom. That gets canceled. And then this equals x. So let's just say, okay, x equals 3.9 times 10 to the negative 6 molarity, and let's now play the 5% rule, where we take that number and divide it by the initial. It's always the initial. So 3.9 times 10 to the negative 6 divided by 0.0028 and times 100. Hopefully that number is 5 or less. Oh boy. 3.9 times 10 to the negative 6 divided by 0.0028 times 100. Oof. Okay, it's 0.14%. So in this case, it passed the 5% rule. I'm just going to erase this math. So now I don't have to go back. I can say that this is the x value. So that's just x right here. So now I know the concentration for that conjugate base, C6H4, CO2, 2 minus, is 3.9 times 10 to the negative 6 molarity. Now, when you're actually doing the math, you do incorporate that x value. So I would say, okay, let's just see if we're going to change our value. 0.0028 minus 3.9 times 10 to the negative 6, and then 0.0028 plus 3.9 times 10 to the negative 6. Let's just see if these numbers will change. So they might not. 0.0028 minus 3.9 times 10 to the negative 6. If we round, it's not changing. So I'm going to keep it as that. And I mean, it will change after 3 sig figs, but I'm just going to keep it as 2. And then 0.0028 plus 3.9 times 10 to the negative 6. Same thing. It's still 0.0028. So I'm just going to leave those. Okay. And now there's one thing. Remember that if you have, so maybe I'll check this one off. Remember, if you have H3O plus concentration, you secretly have OH minus as well. So that's the one that, even though it was not found on any of these balance equations, they still want it because they say calculate the concentration of each species. So I'm just going to, pause the video if you need to. I'm just going to get rid of all this. And remember the formula between H3O plus and OH minus. Kw equals the concentration of those two multiplied together. So you have hydronium times hydroxide. And if we want to solve for OH minus, we just have to divide by H3O plus, right? So what I'm going to do is I'm just going to set that up for myself. I'm going to pull this down. And that's my little thing right there. The H3O plus, we already stated, was 0.0028. And the Kw is a constant value that should be memorized throughout this whole chapter. It's 1.0 times 10 to the negative 14th. So 1.0 times 10 to the negative 14th divided by 0.0028. This all equals the OH minus. And maybe I will put this over here. And then I'll just link this one at the bottom. OH minus 2 sig figs, if anyone cares. 1 times 10 to the negative 14th divided by 0.0028. I get 3.6. That looks good if we have 2 sig figs. 3.6 times 10 to the negative 12th molarity. Check that one off. Box all of these concentrations off. And we are done. Those are your 5 answers for this problem. Oh my goodness. I really hope this helped, guys. Let me know in the comments. Subscribe to the channel. And I hope to be seeing you in later lessons. Okay? All right. Have an awesome day. Bye-bye.